We're going to go ahead and solve this integral using contour integration. Contour integration is an integration technique that you learn later on in complex analysis. And it involves imagining our function now in the complex plane, where we can use Cauchy's residue theorem that tells us that the integral about a contour is going to equal to 2 pi I times the sum of all the residues. And here's the formula to find the residues of each function, where z is going to be the pole and n is going to be the number of singularities in the function. And to simplify, think of the pole as a vertical asymptote of a function, and the singularities are basically their multiplicities. All right, let's get started. Now, just so you know, you can totally solve this using different methods like trig substitution, but I think contour integration makes it really fun. So first, let's go ahead and establish our contour plane. On the x and y plane, this is going to be defined from -infinity to infinity. So in the complex plane, we're going to go ahead and draw a half circle about this contour that's half the circle above the x-axis. So in this case, our radius is approaching infinity. So now we're going to go ahead and start integrating about this contour, and I'm going to go ahead and change my variables now in terms of z's, because that's how we like to define complex values. And now we can go ahead and factor out the bottom. So this looks like it's z squared minus 2i. Whoops, not z squared. It is going to be z minus 2i, z plus 2i. And both of these are going to be squared. You can go ahead and kind of do the math there just to double check that that is going to be correct. So it looks like we technically have two poles. One of them is going to be 2i, the other is going to be -2i, and they both have a I almost said multiplicity, but they both have a singularity of 2. So I'm going to label that as n is equal to 2. Now let's check this out. 2i is somewhere inside the pole. -2i is on the outside. So you're going to see very quickly that we're not even going to worry about this one. So if you recall the residue theorem, we know that this integral about a contour is going to equal to 2 pi I times the residue of our poles of the function f of z. So in this case, the only pole that we have is going to be 2i with the singularity of 2. Okay, so now we know that we have to go ahead and solve this right side, but we need to find out how to find a residue. So let's not forget that a residue at some point k of a function f of z is equal to 1 over n minus 1 factorial of the limit as n approaches, whoops, that shouldn't be n, it should be z approaches your specific pole of z minus zk to the power of n. Actually, I should change that up because it's technically a derivative. So the derivative of d over z, and this is n minus 1, n minus 1. So whatever your pole is, whatever the singularity is, then we subtract 1, and that's how many times we have to take the derivative of this function of z minus zk to the n power times f of z. Okay, so all we really need to do is now go ahead and plug in everything into this equation for our function. So in this case, remember the only pole that we have is 2i, and it has a singularity of 2. So plugging into this formula, we have 1 over n minus 1. So this is 1 over 2 minus 1 factorial. The limit as z approaches 2i of the derivative of 2 minus 1 over dz 2 minus 1. So if you simplify that, that's just going to be the first derivative of z minus 2i to the power of 2 times our f of z. Our f of z is the function that was given to us in the beginning. So we have 1 over z minus 2i squared, z plus 2i squared. And the reason why we have this is so that z minus 2i's, those can cancel out. So now let's go ahead and talk about the next step that we have. I'm going to put it down here. So simplifying this, we have 1 over 2 minus 1 factorial. That's just 1. So we have limit as z approaches z 2i of my derivative. This is just one derivative of 1 over z plus 2i to the power of 2. Hopefully you'll agree that this is the same thing. All right, so here we go. Let's go ahead and find this. Let's take the derivative. We still have this limit as z approaches 2i of -2 z plus 2i to the -3 times the derivative of what's inside, which is just going to be 1. Awesome. So now let's go ahead and plug in 2i. So this is -2 times 2i plus 2i to the power of -3. And we can simplify this. This is -2 over 4i cubed, or -2 over 64 I cubed. And I cubed is going to be -I. So this is -2 over 64 I. And I guess I can simplify this if I wanted to. I'm going to make it -1 over 32i. Okay, so this is our residue. So going back, don't forget that the equation is going to be 2 pi I times the sum of all the residues. It only, in this case, the only residue was 2i, so it's just going to be 2 pi times I times the residue that we found. So at the end, we can say that this integral, actually, let's do integral from negative infinity to infinity of this function squared dx. This was equivalent to this integral here, z plus 2i squared, z minus 2i squared. And we had said this was going to be equal to 2 pi I times our residue. And this is negative 1 over 32i. Going back to this, I just realized that the I cubed was negative I. So I will go into this step right here. That should have been a negative 64i. So then our problem is going to have a negative 1 over negative 32i. So really, it's just going to be a positive. So going back to our problem, it's not negative 1 over 32i. It's going to be positive 1 over 32i. Awesome. And so now the i's cancel out, and we have 2 pi over 32, which is going to be pi over 16. And that's how you integrate using contour integration.